Hello, I'm Valosek. Welcome to our poster. I have nothing to declare. Let's start with the introduction. Spinal cord fMRI studies use vertebral levels for spatial normalization to the standard space and to perform group level analysis. However, the vertebral levels on the right and spinal levels on the left are not necessarily aligned. For example, you can see that the C7 spinal level is not situated in the C7 vertebra. Additionally, the correspondence between vertebral and spinal levels varies across individuals. For example, Cadot et al. Showed in their study that the position of the C7 spinal level varies relative to the position of the C6 vertebral body across individuals. Our objective was as follows: develop a method for automatic, level-specific segmentation of cervical spinal cord nerve rootlets from T2-weighted MRI scans. Moving on to the methods. We use data from two open-access multi-subject datasets, namely from the spinal cord head position MRI dataset and the spine generic multi-subject dataset. For both datasets, we use T2-weighted fast-spin echo images with 0.6 to 0.8 mm isotropic resolution. To facilitate the creation of manual ground truth labels, the segmentation model was iteratively trained using an active learning approach. First, we manually segmented spinal cord dorsal nerve rootlets on 12 images from the spinal cord head position MRI dataset and trained the first binary model. Then, the first model was used to segment additional images from the spinal cord head position MRI dataset. These segmentations were visually inspected, manually corrected if necessary, and used to train the second model. The second model was used to segment images from the spine generic dataset. These images were again visually inspected and manually corrected if necessary. Then, the binary segmentations from both datasets were combined and manually modified to incorporate spine level information, assigning one label to each class. For example, number 2 to C2 rootlets, number 3 to C3 rootlets, and so on. The final multi-class model was trained on 31 training and validation images. 5 images were used for model testing. These 5 images were manually segmented by 4 raters, and a consensus reference segmentation mask for each image was produced using the staple algorithm. The final multi-class model was additionally tested on 3 datasets unseen during the model training. The first testing dataset was the spine generic single subject dataset consisting of a single subject scanned on 19 sites on scanners from 3 vendors. The second testing dataset was the kurtosis neuromod dataset, which contains a single subject scanned on the same scanner 10 times. The third testing dataset was a private Marseille dataset containing 4 subjects, each with 2 sessions. The evaluation of the segmentation performance was done using the dice coefficient. Then, we obtained the spinal levels from the nerve rootlet segmentation as the intersection of the nerve rootlet segmentation and the spinal cord segmentation. Finally, we used the spinal cord toolbox to compute the distance between the pontomedullary junction, PMJ, and the rostral, middle, and caudal slices of each spinal level along the spinal cord center line to take into account the spinal cord curvature. Okay, moving on to the results. Here we have an example of the reference ground truth mask obtained using the staple algorithm and the segmentation obtained using the proposed segmentation method named as NN-unit. The final model achieved a mean test dice of 0.67 across 5 test images. This figure shows the distance from the pontomedullary junction PMJ to each spinal lever for 5 test images. In red, green, blue, and yellow, we can see 4 manual raters. The ground truth staple segmentation is shown in light gray, and the segmentation obtained using the developed segmentation model is shown in dark gray. Manual raters demonstrated excellent mutual agreement with the mean coefficient of variation across raters and testing images below 1.45%. The spinal levels obtained from the ground truth staple segmentation, shown in light gray, did not significantly differ from the levels obtained using the developed segmentation model NN unit, shown in dark gray, for any of the testing images. Here we have results for the first testing dataset, a single subject scanned across 19 sites. The obtained spinal levels correspond well across sites. When excluding 2 sites with low contrast between cerebrospinal fluid and rootlets for C7 and C8 levels, marked with red crosses in the figure, the mean coefficient of variation across levels and site was below 1.37%. This figure shows results for the second testing dataset, a single subject scanned 10 times on the same scanner. The obtained spinal levels show a good agreement across all 10 sessions with an intersession coefficient of variation below 2.29%. Finally, we have results for the third testing dataset, 4 subjects scanned on the same scanner each 2 times. The spinal levels exhibited excellent correspondence between sessions with no statistically significant difference between sessions for any subject. The proposed segmentation model is implemented in the SCT DeepSeg function as part of the Spinal Cord Toolbox, SCT. In conclusion, this study introduced a deep learning model for the automatic segmentation of spinal cord nerve rootlets from T2-weighted MRI scans, and a method for identifying the corresponding spinal levels based on the rootlet segmentation. The methodology is open source and available in the Spinal Cord Toolbox SCT 6.2 and higher. Thank you for your attention and stay tuned for the upcoming SCT course, which will be held in November this year. You can also download the latest version of the SCT, which contains the proposed segmentation method and many more new features.